So my name is Stephen Callahan. I am a senior principal engineer with the Amazon Infrastructure Services. And so I'm working with the physical routers and switches. This talk came about because I was part of a presenting team last year who talked about the things that AWS has done in their physical networking in the past. And the feedback from you, our customers, was that let's talk a little bit more about what we're currently doing and where we're going to the future. And so this is why this is our journey towards intent-driven network. As a kind of a quick introduction, obviously I'm excited to be here. We don't talk about this much, right? This is not something that you're going to see at most of the reInvent talks. I'm a network engineer. I don't work in the cloud, I work underneath it. And if you know what this cable is, and it's an RJ45 connector on one end, and amazingly to me, I found out only a few months ago, these come in Type-C. So I have no more dongles in my life, which I'm happy about. But most of the time, I'm actually working on the software that maintains our network. And so there's devices that exist there, and the software that sits on top, and the software that maintains that on top of it again. And when I think about what the network actually is, it is a layer of systems between the devices, the control plane, the management plane, the planning. All of these things are integrated systems. And I wouldn't be here if we didn't have reliability. So this is one of the things that's ingrained in all of our people, is that we want to have high reliability and high availability in all the things that we do. So these days, technically my title is just technologist, because we have to go across all of these domains. And so as a bit of an agenda of what we're going to talk about, when I think about how we're going to evolve the network and how things are going to grow, we have a set of goals that we want to achieve. And we have a set of capabilities we've built over the last 10 or 15 years that we're using to achieve these. And one of the things we're doing now are intents. These intents give us new capabilities, a new direction for us. One of the examples that we did, and the use case we have, is the ultra clusters. And so we did a new version of ultra cluster this year. And so I'll give you a little bit of a walkthrough how we did it and why intents made a difference. Then we'll go into the control plane that optimized topology of ultra cluster is required, and then the management plane that sits on top. And then there's a little bit of automated reasoning, which is something that we're also really passionate about, and the changes that it can make are quite large. So it is important to kind of, before we get too into the details, and just clarify. Like I said, I'm an infrastructure engineer. So physical routers, switches, cables, data centers, that's my realm. There are other people here from EC2 networking and edge networking who can talk all day about hyperplane and global accelerator. That's not me. You want to talk about a router and look at the components inside? That's what we do. And so every year, we get a new infrastructure map. And I look at this, and I'm kind of planning in the future, and I always see, okay, well, there's more regions in the last year, okay, and there's going to be more again. But there's also more features. We've added local zones. They add a new complexity to things. And so things are growing in scale, not just in more locations, but also in more features, more things. And this is a slide I lifted. I think it was from Peter's talk last year, where we talk about availability zones. And this is where I live. And there are some things that are here within this that I look at, and the promises that we're making, the isolation with one or more data centers, how they're connected and how their redundancy is between these. These are things that are important because they're public promises that we make. And I wanted to try and find a way of how do we take these and internalize them in our own systems such that we know about this. And so going on any development cycle, this is a favorite slide of mine. This picture is on the wall in my office, where we talk about not just the minimum viable product, which is the origin of this, but the minimum lovable product. What actually is going to be useful? What are people going to enjoy having as opposed to just working? And the whole concept is that you start increasing benefit. But on the bottom slide, you'll see, well, it's only about step 3 do people start to get somewhat happy. And then step 4, it's really happy. But to get beyond that, occasionally you need to reinvent things. You need to look at motorbike worked. Maybe it's time to move to a car. And so then I look at, okay, let's look at other areas. What has had this occasional reinvention? And so I look at passenger aircraft. This is a plane from the 1940s, one of the first commercial passenger transatlantic aircrafts. Purely human operated, no automation, no assistance, no sensors. This is what we have today. And so there's more people, there's more traffic, there's more planes in the sky. They are more complex things, but they're also orders of magnitude safer. So the plane on the left wouldn't survive in the modern world. It's had to modernize. But there's orchestration, there's redundancy, there's lots of intercommunication. So these are the things that have modernized that platform and moved things along. And so when we look at evolving the network further, the goals that we have are mostly the same. We want to increase our availability. As an operator, someone who's looking at a network, I want to increase consistency. I want to make sure I'm kind of stamping out any variability that exists. That's important. I believe it's important to customers and it's important to me. I also want confirmation. When I make a change, did it actually happen? Is it done and done forever? Or is there a chance that there may be problems? Obviously, things have to be scalable. We show getting larger in multiple dimensions. And we also don't want that scale to increase our operational burden. So we want to kind of constrain our operations, limit that such that it's easier to operate this ever-growing network. And so with every goal, there's always a set of challenges. And so yes, we have more complex networks. There are more device types as we move to newer generations of equipment. We've got new topology types. They come across the new more products that we have, like ultra clusters too. We're also changing our constraints. These availability goals, we want them higher. We want lower latency. We want lower jitter. And we also have more locations and more people. And when you have someone who's a 20-year experience in one part of the world and a 2-year experience in a different part of the world, it's very unlikely they're going to think about the same problem in the same way. And so not only do we have different people, but also there's different standards in different regions. And so we have to account for this and how we grow and scale something like the network. Now, in terms of physical hardware, we've owned our hardware design and owned the components that live on these devices for years now. And what's in them is not just designed by us, but there's also components here which are specifically for us. And so, for example, this board here handles the updating of all of the optics in parallel. Industry standard, normally you can update one transceiver on the box, you move to the next one. 32 cycles to get across the entire box. That's a bit too long for us to take it out of service. We'd like to move it a little bit faster, like to be a little bit more deterministic, and so we developed a board that update all 32 at the same time. And similarly, the box on the right, it's a different color because it serves a different purpose. And you'll see on the ports on the right-hand side have less air holes than the ports on the left-hand side. And that's because these ports are for external capacity. And so this is where we put our long-range optics. This is also where we house our MACsec hardware encryption module. And so they take more power, they require more cooling, and therefore there's more holes. So we've customized these things for the building blocks. But generally, a green switch is a green switch. A purple switch is a purple switch. We can mix and match. We even make changes with optics. We wanted to put 4 pairs of optics in a standard, 4 pairs of fibers into a standard QSFP. So we designed a new optic with one of our vendors, one of our manufacturers, and we can kind of iterate there. A lot of this comes along because we've standardized on these single chip network devices. We are not a chassis shop. We do not have refrigerator-sized things with line cards. We have the green switch, the purple switch, the red switch. They're all 1 or U, mostly. Purple's 2. But generally, they're 1 or U, and we do racks of them. We also own the entire software stack. So it's Linux-based, like most of the industry, but we've got multiple manufacturers. So one green switch is as good as any other green switch. We've also got multiple ASICs. And so from all the merchant silicon vendors that you know, we've probably got one of them somewhere. And where we spend most of our time is enhancing the routing protocols, making these networks work better the way that suits us. So here's the packaging. It's not particularly pretty, but it works well. And we stamp these things out. Racks of 32 switches is our standard cell. It's our standard unit that we deploy. And the systems that need to sit on top of this is all of these cables, all of these devices. We need to have the systems I mentioned before to be able to triangulate. Because as Werner, the CTO, says, everything fails all the time. And so when it does, we want to identify where that is quickly and take it out of service. And so these are the capabilities that we've built up between the hardware, the software, and the services that sit on top to maintain this network. I'm a fan of, let's say, stealing outright from internal wikis when it comes to preparing these talks. And this is a tenet. This is one of the core principles of the team that I'm on within the data center networking space is simplicity scales. And it's kind of expanded out that what we want to do is we want low complexity. But if you've low complexity and you've low innovation, you're kind of restricted in what you can do. You can only say yes to particular opportunities that fit in the stamp out things that you've made, each cookie cutter you've made. If you don't control that complexity and just start adding more and more things, you will end up frustrated. You can't innovate, you can't do anything else because we're limited in this and there's too many of them. The problem is if you try to innovate from that phase, you say, we need to make changes, we want to move forward, you will end up overwhelmed. Now you've got many variations with too many things and you're basically fighting fires all the time instead of thinking ahead and preventing them. So where we want to live is in this lower right quadrant. This is high levels of innovation, being able to say yes to new opportunities and new things we can do without increasing our complexity. Intents are the way we think we can do this. So last year, J.R. and I were here, like I mentioned, the feedback from that talk, where we went into way more detail on the hardware and software that we had. The feedback from that helped with this. So let's get into intents. So one of the last slides in that talk from last year was that we were thinking about intentful management. And intent management was not thinking about what was happening, but dealing in the expected behaviors, what we expect to happen. We wanted something that was hierarchical. And so something that goes across multiple domains, whether it's the device, the zone, all the way up to regional and planning. Something that can span all these domains, bring them together. We also wanted these changes to be closed loop. Like I said, I like completeness. I like confirmation when something is done. So having closed loop intent systems would give us that capability. Except it wasn't quite the future. It was what we were already working on last year and what we're going to talk about this year. So I've said the word enough times. It's time for a definition. So again, lift it straight off the internal wiki. An intent is any behavior we expect of the network. Now I've highlighted these things. One, intent is capitalized because we have specific definitions of this internally. We also deal in behaviors. And so this could be what we expect the network to do, and we define these things in a declarative manner. Much like, if I look at the industry, if I look at the RFC that was published last year from the IETF, slightly different but similar concepts. We have goals and outcomes, and we have a declarative manner. And so these are behaviors that we're talking about. Okay, why would I use intents? What's the benefit? And the core for me is intents bring consistency. When I put intents at the center of how we make changes and how we design the network, I know that any system that's communicating with those core intents is getting the same information. I'm not requiring someone, a person, to go and make a change here and then to remember, I need to change this system and this system. No, the intents flow out from the center. This gives a level of visibility that when we make changes, the systems are already updated. I know what's happening in real time. This is also important when I get to automated reasoning later, is we want to push testing, much like in software, as far left as we can. Do the testing early. And by dealing with intents, we've basically got a ledger of the expected behaviors of the network, and we can do that testing far earlier than we could before. And then finally, again, operations. I'm thinking about how do we maintain this network? How is it going to grow? What's going to be needed to make sure this remains safe, continues to be safe, and continues to scale. So again, network engineers in the room, let's bring it back down into this. This is the way generally we would think about changing the network. I have a set of networks on the right-hand side, and I've got people or maybe systems that are wanting to make a change. And generally, that operator is going, okay, I need to change the policy. I wanted the network to do this. That means I need to set a local pref, a change of community, add a med value, something like that. They're in the policy. They're in the route map details. If I change this over to intents, all that work has already been done. We have defined, in this case, an intent called non-transit. And this non-transit, in our terms, means if you've got two buildings and a connection between them, the only traffic on that connection between the two buildings should be serving those two. If you have a downstream building that's connecting in, that traffic should not go over here. And so this is an intent that we've created. We've done this years ago, at this stage. It's defined how we want to do that. And so now an operator or a system, instead of saying, I need this particular behavior, this is how I'm going to configure it, it applies it to the intent system. The system, thankfully, not always a human, applies it to the intent system, and that flows out to the rest of the systems that we have. And you can see here on the top and the bottom, we've got networks that are intent native, and then in the center, we've got ones that are not quite there yet. They haven't quite been converted, and so the intent system, the center box, needs to communicate with both of these. And then over time, we expect we'll convert all of these systems into something that's intent native, and therefore, this is a nice, clean slide where operators are talking to an intent system which is maintaining the network for us. So if I go back to that slide on availability zones, some examples. Kind of talked in abstract a lot here, so what do I mean by this? Here's one that's on the availability zone slide, but it's actually quite hard to think of in terms of like BGP policy or a network engineer. It's pretty reasonable to expect if you've got two instances in an availability zone and you want traffic to go between them, the traffic should never go to another availability zone. We may have multiple buildings in this AZ, but to get from one to another, it should stay inside it. There's no one line of policy I can write to do that. That's quite a complicated intent that we've created. The one that I mentioned before, this non-local, this non-transit. I may have 3 buildings up the top which are fully built out and have been there for years and lots of capacity, and then we add a new building that doesn't have quite all the capacity it needs yet. And so we want to make these orange link only carry local traffic. And at some point in the future, we'll say, the building is now large enough, the capacity is now large enough, we want them to be regular links. And so applying and removing intents is kind of what we're looking at. And then finally, we're always testing the network. We'll find elements, we'll take them out of service, we'll do intrusive testing, we'll make sure that it's working correctly, we'll put it back into service. And so it would be nice if when we put something into testing state, everything knew it was in testing state. So we didn't have alarms going off that there's too much traffic, or it would be intents enable all of these systems to know this segment is in testing state. And so we've broken down intents into a couple of different categories. These are just the 4 we started with. In terms of an operational intent, this is relatively easy. Is a device, should it take traffic? Should it not? Should the protocol be enabled? Should it not? In terms of routing, we need to teach the system what do we mean by a preference between different virtual IPs. If I have a primary and a secondary, we need to know what they are. At the end of the day, we're maintaining a network, so there's prefixes. And so these prefixes are going to be originated from somewhere, they're going to be learned from somewhere. The system needs to know that prefixes exist and they're a core component of maintaining a network. And then finally, I mentioned before, there's systems on top of systems that maintain this kind of multi-domain network. And so I've got failover times. If I have a low-level system that should fail over within 50 milliseconds, and at some stage we have to change that to 500, something else should know the threshold is no longer the same. It's even worse in the opposite one. If it was 500, it's now 50, and my threshold is still 500. I may be failing my requirement and not know about it. And so this is where these intents, in terms of recovery targets, in terms of failovers, are all propagating out from the center. So, use case. Machine learning, it wouldn't be a talk in 2023 if someone didn't bring it up. So if I look at this, 3 years ago, Dave Brown at an unfortunately virtual reInvent announced P4 instances with 400 gigs of capacity in every instance. The next year, Adam at the stage in reInvent did TRN1 with 800 gig. So you think you see where this is going. Peter, the year after, TRN1N at 1.6 T per instance of network connectivity. And then Swami in July did P5s with 3.2 T. I am slightly suspicious that there's been 4 launches with 4 different people. I don't know what the next one's going to be, but maybe they have to toss a coin, I don't know. But when I look at this from an infrastructure standpoint, this is only going one way. I don't know what the future holds, but I know this graph is going one direction. And so when we looked at ultra clusters, we needed to do something different for P5. It was kind of exceeding the requirements that we had put for ultra clusters in 1. So ultra cluster 1 came out for P4. It's 4,000 GPUs, and each instance had 400 gig of capacity. So when we looked at Ultra Clusters 2, what needed to come next, we wanted to see, well, we could just change the box and make it better. 4 times the box, 4 times the capacity. But we also want to go, well, what effect is the network having on the workloads? We know these are machine learning workloads. We know that training is happening. So what can we do to make this a better experience? And so we set ourselves a number of goals. The bandwidth, yes, 3.2T. Okay, it's going to go up, but for now we've got 3.2T. Scale, the 4,000 GPUs that we had for P4 was going to be 20,000 for P5. And so we were going from parts of buildings to entire buildings and potentially multiple buildings for the next gen ultra cluster. From that paper and from other sources, we knew that if we could drop the latency and reduce the hop count, so the number of devices from any host to any other host, from 7 to 5, we could keep our half round trip time under 10 microseconds and improve the performance. And then finally, we still wanted this consistency. We wanted non-blocking capacity. And so that's any host can talk to any other host at full rate. There's no oversubscription, there's no rate limiting, it's fully open. And so this led to Ultra Cluster 2, which as a marketing slide is amazing. Okay, we got 20,000 GPUs, we've got 3.2T EFA. It looks very similar to the last slide, but as an infrastructure, no, it changed a lot between 1 and 2. And so what Ultra Cluster 1, in terms of goals for Ultra Cluster 2, we knew we needed 20,000 GPUs in one data center. We knew we wanted to start with what the medium variant. And so the 20,000 was medium. We would probably need a small, we'll probably need a large, and so on. But this is what we started with. But when we looked at the topology, we looked at what we wanted to do. To do this, we needed a new routing protocol. So to meet the challenges of Ultra Clusters 1, we couldn't use the same techniques we'd used with, to meet the challenges of Ultra Cluster 2, we couldn't use the same techniques we used for Ultra Cluster 1. And to do the custom routing protocol, we needed the new management plane as well. And overall, we set a pretty big goal of doing tens of petabits in under 10 microseconds. That was kind of the main thing we were trying to do for the project. So the main physical differences are, on Ultra Cluster 1, we've got our top of rack switch. This is standard across all of our racks. And we connect the top of rack switch into these cells. And so these cells are the first 2 stages of what's known as a cloth or a clove fabric. And so this is a leaf spine architecture where the top of rack switches connect into the cells are connected together by the spine. And this is what's known as a 3-tier cloth. So there's 7 hops. If you have a host on the bottom, to go all the way up and all the way back down, you have to go through 7 network devices. So our challenge on the right was, there's going to be more switches. We have more racks. We have more top of rack switches. And we wanted to reduce this to 5. And so this is now a 2-tier cloth. So we've got top of rack, T1, T2, T1, top of rack. And we needed to horizontally scale these backplanes. And now every top of rack switch is connecting into multiple backplanes. And so by doing this, with this topology, we knew we could meet all these goals. But scale is always the factor that's going to come along, so let's have a look at the scale. In terms of the medium, the one we started with was 3,500 switches and 135,000 links. This is what we were putting into one building to meet Ultra Cluster 2. The large one, we knew we needed 7,000 switches and 266,000 links. Numbers go up quite quickly. When we get to extra large and beyond, this is, again, only going to increase. And so here's the routing design for Ultra Cluster 1. It's a combination of techniques. It's using OSPF, it's using BGP. Generally, these are the techniques that you use when you want to scale a network. You don't want a singular OSPF domain that can do everything. OSPF does not scale to 3,000 or 7,000 devices. So you have things like OSPF areas, BGP, route reflectors, or eBGP separation. So we do eBGP separation between buildings, but internally we're doing iBGP. Sometimes we do confeds. The downside of all of these techniques is their effective mechanism is hiding information. And so from one OSPF area to another, you're not advertising all of the information, just a summary. Let's have a look at the topology of Ultra Cluster 2 and see what happens. And so here's my 4 top of rack switches, 2 backplanes, and we're going to send packets from router A to router D. By the way, I use router, switch interchangeably. So this case, everything is working, goes over to D. As Werner says, everything fails all the time, and so this link is going to go down between backplane 2 and router D. And so if A were to blindly forward this information, if A did not know that this link had gone down, the traffic would get to backplane 2 and stop. Now, it would either get dropped, or it might take a longer latent path, heal across another domain, but it would, violate our requirements of 10 microseconds and reducing the hop count. And so what this means is we actually need a singular control plane domain for all of these devices. So every device here needs to know about every other device and every other link in the entire fabric. That doesn't work with the traditional routing protocols that we had, so we created a new one. And so this is CIDR. Yes, we're a bunch of nerds. It's a play on CIDR. But, So where this sits is CIDR sits as the new routing protocol. So it's at the top of our stack that's here. We have the requirement, it's got to be a single control plane domain. Everything needs to know about everything else. We wanted a hierarchical control, because managing 7,000 devices is not easy. And so how can we make this network appear much smaller than 7,000 devices? The completeness was going to be key. We wanted to make sure we weren't going into a world where we'd make a change and it would slowly roll out. This is a singular fabric. This is a thing that does a single purpose. And so let's make sure it operates as a singular thing. To do that, we also want to be SLA bound. If we're going to have completeness, I need to know what's going to happen in 1 second, 10 seconds, 30 seconds. We need to create these SLAs around making changes. And then finally, because this needs to exist in the world that we have, we wanted to use eBGP to connect CIDR to the rest of the network that we have. Okay, so you're designing a control plane protocol. Where do you start? Well, the first option is you got to make a choice in terms of, are you going to do a distributed or are you going to do a centralized one? So distributed, like OSPF, statically stable. It's great. If the device reboots, it comes back. It has all the information it can forward on itself. That also means if it goes down, there's no amplified effect radius here. The scope of impact of a failure is constrained to the area that happens. But we also like the visibility and the determinism of a centralized fabric. Let's say something like OpenFlow, where we know everything is happening. We can have full visibility. And so we kind of looked at this, and of course the answer is always secret option number 3, and it's to do both. And so we created a hybrid. And so we have the benefits of the distributed with the visibility of the centralized. Okay, next step in terms of building a control plane protocol is we need to look at some fundamentals. One of my favorites that I come back to all the time is CAP theorem. You've got 3 things: consistency, availability, and partition tolerance. And this is one of the fundamentals of system design. Getting all 3 is effectively impossible. Some mechanisms work well in steady state, but to have all 3 in failure, it takes a lot of work and is not very easy to do. In fact, there's a tiny little hole in the middle of those 3 overlap, because if you don't get it right, you may have none. And so we wanted to make sure we got it right. And how you do it is you build mechanisms. And these mechanisms focus in one of these 2 areas. And so any one mechanism can give you consistency and availability, but it's probably not going to be great for partition tolerance. And so it's a multitude of mechanisms that's needed to build up a system like this. In terms of consistency, the general wisdom is there's 2 types. Eventual consistency, the standard S3 is like this. If you make a change, until that change is complete, you may get answer A, you may get answer B. And so this is how something like maintaining an OSPF network of 7,000 devices, if you need to change every single one of those devices, by the time you get to the end, something will have changed. Okay, it's going to take a while, and so that's eventual consistency. Strong consistency is everything is on the same thing as quickly as possible. And you do that with commit sequences. And so in CIDR, we have a commit sequence that every device is on version 47. And now we're all going to move to version 48. And so that's how we get the completeness that we needed from the control plane. In terms of availability, this is the control plane. So this is the ability to take on new work. So I want to make a change. Is the control plane letting me take a device out of service, take a link out of service, make the traffic go west instead of east? We have this with our hybrid control plane. And so if we have issues at one layer, we can take a break glass and go to the layer beneath or the layer beneath. And so these are the mechanisms we have for making sure the network is always available for us to make changes. And then finally, we look at partition tolerance. Everything fails all the time, and we want to make sure that when it does happen, that not only is the system graceful under that failure, that we get into this split brain world and both things work correctly, but when the recovery happens and things have to come back together, that it's graceful upon recovery as well. And so we do this by intelligently placing the leader nodes where they need to exist. And then when that recovery happens, we have a consensus mechanism. And so we gain consensus back. Hey, we're all on 47, and we all move to the new state. We also had a few extra things we wanted to throw in here with Cider. We want prescription. We know where every link, every device, every cable should be. We don't need discovery mechanisms to learn what the neighbor is. You either are not the correct neighbor. And so that level of determinism is kind of baked into our designs and our software that maintains the network. So let's make a control plane that works with that. We also wanted additional security. We don't want a rogue device getting plugged in and potentially forming an adjacency. So what we've done with Cider is every message is signed and validated. And so anytime we're making a control plane message, we're confident it's coming from the right source and that the destination has received it and it's valid. And then finally, one of the things we wanted, automated reasoning, which I'll give the example towards the end, we can have it in the routing protocol itself. It doesn't have to be at higher level abstractions. So if we can add more testing and verification into the protocol, we believe it brings more benefit. So how does Cider work? Like a lot of distributed protocols, we've got devices, we run the Cider daemon on the device, we've got the connectivity, and now we have a fabric. This is all of these devices have connected. We've told the fabric, you're prescriptive, here's your topology table, this is what it should look like. We then want to make changes. So this is our hybrid centralized view. And so any changes coming into the fabric are going to go through the supervisor. So we have that visibility, we have that awareness of what's happening through the supervisor. And the supervisor has an agent in the fabric, which we call the SFC, or the Cider Fabric Controller. And we hook these things up. And this is where our partition tolerance comes in to make sure we're placing them in the right place, and we can migrate between different supervisors, in a cluster or between the fabric controllers. The four main things that we do with Cider and how we propagate information is we want this topology table. So we want to propagate to the device, this is the entire topology. These are all the links and nodes that should exist that you should connect to externally and internally. We also have the policy. Which way should traffic route? Should we allow a default from the north? Should traffic go west? What traffic? We propagate this in policy tables across all of the devices. We're running a network. Prefixes are at the core of the business, so all the prefixes that should exist either be advertised or received or be originated, all from the prefix table. And then finally, because we knew we're creating something new, we want to make changes, we also have the ability to change the runtime in the table itself. So the entire fabric can go from runtime A to runtime B as part of a commit sequence, much like you're shutting down a link. This made operations a lot more simple for us. So we've got this message bus. This is where the message is going to come in from the SFC, get propagated out. Right now, we're doing hop-by-hop distribution. I added the little star up there because we can do dynamic flooding, we can do more sophisticated things, but we haven't had the need to yet. Everything's running over TCP, and the goal of the message bus is to have these tables shared across every device. We've also, on the devices through the message bus, we have a custom path calculation. So we don't have to do basic Dijkstra like you would with OSPF. We have weighted cost multipath native within the protocol. We can also do different things at different layers. Maybe the weights on this device should be for that layer over there, or on a different device should be at a different link. And so we've got this path calculation agent, which we can change over time. Like I said, in security, every message we have is signed and validated. And even with that, we're getting an end-to-end message propagation in order of 10 milliseconds. Now, it's not the 10 mics that we get in terms of the physical links, but for going up and down across a few control planes, I think 10 milliseconds is pretty good. And so how we do this distribution is we want to lazy load these tables. And so the first thing we're going to do is propagate version 48. We're going to make sure the devices have kind of time to reason about this to make sure, yes, I'm not being asked to do something that I can't do. Once that's happened, we're then going to propagate a commit message, which is going to apply the new state in a coordinated fashion. So the entire network is moving from version 47 to version 48. Once that's happened, we're then going to come back and check, did everything go successful? Does anyone have any issues? If they did, the network would automatically roll back. We'd go back to 47. Device over here has a problem. We'll go back to 47. We'll figure out what's going on with this device, and then we can move over. And this way, we've got that completeness. It's not that one device is being left behind or a link is different. The entire fabric is now working together. So much like from wiki pages, I also like to just give exact outputs. So this is from a running fabric. What you can see here is everything is transaction-based. So the last transaction used to change this fabric was 25,560. Here are commit sequences, and so the entire fabric is on 9447, and if we were making a change, this would say 9448. We would be proposing a change to move ahead, and it's always nice to get a confidence boost that the fabric is actually running, so we added that in there, which is good. And then on the right side, we're going to talk about the tables. And so you see the 4 tables we talked about, and we've got a current context and we've got a shadow. And the shadow is for the proposed state. So if we were changing, let's say we wanted to change the policy table, in the policy table sequence under the shadow context, you'd see 15 instead of 14. The last step that I said in terms of connectivity was that we wanted to make sure we had eBGP connectivity. And so here's my physical setup, my CIDR fabric on the top. I've got network A and network B. And if I jump over into the logical realm, on each of those edge devices, I've got a BGP terminator. Now this is not a traditional BGP full stack. It is handling my BGP messages, so it's doing all my updates and withdrawals. But generally what its goal is to do is to pass this information up into aggregators, which exist on the SFC. So the SFC has a virtual context for each of these aggregators, kind of like peer groups would do on an individual device. But what this means is there's a singular best path for the entire fabric of 7,000 switches, which means I have one place that I'm doing my BGP policy. I'm then using CIDR-D to propagate that out to the rest of the fabric. But as an operator, we've now taken a fabric of 7,000 devices, and it effectively looks as a singularity. There is one BGP context for the entire data center. And if we want to send traffic north, south, east, west, we only have to do it in one location. Super powerful in terms of operations. To do this across multiple domains, we're kind of looking at one device, or sorry, one fabric. And earlier on, I made some kind of comments that if you make a change, well, what about the other things that exist? Or how do we coordinate across multiple CIDR domains? And so this is where AIDN comes in. So the AWS intent-driven network. And this is our management plane that sits on top of all these control planes. So if I kind of go back to this slide, AIDN is sitting on this intent there across all of those domains. The device and the zone is kind of where CIDR is going to exist, but we still wanted something that was going to connect my regional, my planning stacks together. And so if I just pick one of the benefits that I kind of called out earlier in terms of coordination. So this coordination, if I'm making a change, it's kind of critical that both the controller and the router control plane gets that information. So it's actually going to affect the change. But it's also important that our telemetry system knows that there's now going to be customer traffic on this link. If you see errors, you should alarm. Or for our planning system to know, we've now started shipping traffic on this span, which was previously quiet, which means something else is, we're moving traffic around. And so when we make these changes, we want to distribute this information across all of the different systems that want to know about this behavior. And so we talk about entities, we talk about different abstractions we can use. I've talked a lot about devices. And again, I'm a physical guy. I've got routers and switches, and I think of devices. But I've also got groups of these devices. Maybe 16 of them are performing the same role. Or the fabric I mentioned in CIDR. I've now got a singularity for this fabric. And so as well as the abstract entities that exist, I've also got the connections between them. So the links that are there, the spans that connect different data centers together as a group of links. And so all of these things can have intents associated to them. We're not just looking at individual devices or links, but we can have this hierarchy and this abstraction. So what the AIDN system looks like is we've defined these intents in sets of documents. We've defined the entities in a hierarchical way, and we create an association. So we say this entity, we would like this behavior, this intent to be connected to it. In the center of the AIDN system is the authority. And this has the ledger of all of the previous associations that have already been happened to the network. So we make a new intent association. That coupling of an intent and an entity gets propagated into the authority. The authority then has a set of adapters. And these adapters each have a specific purpose. So my yellow box is my telemetry system. My pink box is my intent native system with my supervisor. And then at the bottom right, I've got a network that's not intent native yet, and so the adapter has got a little bit more intelligence, it's a little bit thicker. And so the subscribers connect into the adapters, such that any time an authority is propagating this information out to the adapter, the telemetry adapter is sending the telemetry system. There's been a change in this area because of this intent association. Maybe my site or supervisor needs to make a change, and I need to do something else on the network side. And so the information gets propagated down to the network from this authority. Again, I'm going to go steal outright from the code. This is the code that we have for an intent. And so you see here, this is the intent defined to shift traffic away from a device in a CIDR fabric. And so this is scoped to a device. The system's not going to allow you apply this to an entire data center. That would probably be bad. But we'll do it to a device. And this is a maintenance intent, kind of like I mentioned before, the different types. And so the operation that's going to get sent to CIDR, because CIDR is intent native, is depref. So depref this device. I then have a set of validations that need to happen. Before this intent was associated, it was acceptable for the device to either have or not have customer traffic. Maybe just none existed yet, but right now it's okay before the change if either state. But after the change, it should not have traffic. It should be in passive state. Then I can kind of go to my NetFlow system, and I go to my continual validation. Let's say it's 2 weeks after this intent association has happened. It's acceptable for control traffic or test traffic to exist on the fabric, but we better raise a big alarm if customer traffic starts coming onto this device that's not supposed to have customer traffic. I can then go into verification. So from my formal methods and my automated reasoning, I'm going to define invariants. These exist within the intents. I can even go into lab testing. We lab test the system. We want to make sure we've done this check and it's passed, that we can do a device shift. And so these intents, this is how you can see it permeates all of these different layers with all of these custom adapters that send this information to those systems. And how this happens is AIDN is based upon transactions. So I'm going to propose a change. It's going to get a review stage. It's going to make sure that this is acceptable. It's going to be approved. Once it goes to the adapters, it's in this pending apply stage. And so all of the adapters are going to try and apply it. Once all of the adapters come back to say that it's applied, we're happy. The transaction is complete. If an adapter were to come back and say this has failed, I can't make this change, the entire transaction gets rolled back, which means we do not have that intent association. So my AIDN authority is an up-to-date ledger of all of the intent associations that have existed. We do this with a few different things, but one of the good methods is that we have these closed control loops. And so there are inner control loops and outer control loops. So the inner loop is adapter goes to CIDR supervisor, please make this change. The SFC comes back, yes, my transaction has succeeded, goes back to the authority, CIDR transaction has been completed. At the same time, I'm going to send that information to my check system. My check system is my outer control loop. It's receiving the telemetry from the system, and then once that intent has gone in, the message again goes back to AIDN authority. Yes, that intent association has been successful according to the check system. The final section on the agenda I wanted to talk about was automated reasoning. This is an area of computer science we're very excited about because it focuses on enabling computers to reason about large-scale problems and kind of come to conclusions. So generally, we apply this to availability. This is where we care quite deeply. And we want to test our configurations to the maximum extent that's possible. And there's two main techniques for doing this. There's validation and there's verification. And the slight subtle differences between them, that's kind of important in my head anyway, is that validation is, are we building the right product? Have we gone to the customer needs to make sure this product is working the way the customer expects? And verification is, we've defined a set of specifications. In these intents, we have these invariants. Is the product built right according to these specifications? And the way you confirm both of these things is test cases give you validation, and your formal methods give you your verification. So getting into automated reasoning, how can we reason about these large systems? So going back a long, long way, and while Pythagoras didn't work for AWS, he's still giving us key concepts that we look at today. So his theorem proved the square of the hypotenuse is equal to the sum of the square of the other two sides for all right-angled triangles. So this wasn't done exhaustively. This wasn't tested iteratively. Mathematically proven through a theorem with a proof. And so those concepts, while they exist for triangles, can also exist for networks. So we do invariant testing. And so we take three core components: the topology that exists, the configurations that are applied on the network, and the specification we've created. So in every intent, there's an invariant. We can take all of this information, apply the formal methods and proofs that we have, and come to an exhaustive answer that, yes, this invariant is true in all cases that exist. We're able to do this by effectively following the same methods that happen through Pythagoras' theorem by exhaustively proving, well, not through iterating through every test, which would take effectively forever, but we do it mathematically. And by applying this mathematically, we are making a network that's more robust, and we can prevent outages from happening. We do this by inserting this verification step in advance of the authority. So we're able to shift the testing all the way left, such that we're able to do these verification, exhaustive testing on all the policy and all of the invariants and all of the intents that exist before it ever makes it to the authority. So rather than doing simulation or emulation, we do this through these formal methods. This is, AWS has a long history of automated reasoning. The provable security that's being done, Peter's gone through it and how we've applied it to some of the protocols that we have or some of the products that we have. It's also available to you, the customer, in terms of inspectors, like, is my instance reachable from the internet? We can't do that through experimentation. We can't do that through testing. We have to do that through formal methods. And so all of these answers, like, are my ENIs from prod reachable from dev? These are the products that we've exposed. We've now taken those same techniques and we've brought them in-house. So in terms of a wrap-up, it's been a whirlwind. The way I look at these things, the way I look at evolving the network, is it's going to start with what are the customer needs? What are the things that we can do as infrastructure engineers that is going to have a differentiation for the customer, for that machine learning workload, for that the safety of an availability zone? We then also want to work backwards. We want to say, this is the new state that we want to be in. How are we going to achieve that? And then finally, we need something that's going to keep focus on it. We don't want to say something 5 years ago and then forget about it now when we're designing the new thing. We want to take something and capture it and make sure that when we make a change, it's permanent. And so intents is what I think keeps us in this bottom right corner. It means that we have low levels of complexity because we're dealing with these individual intents. We've got this high level of innovation because we can say yes to opportunities like Ultra Clusters 2. We can move things ahead. And intents keep that balance for us where we can increase our availability and also keep ourselves simple. If you want to have a look at some of the physical hardware, we're at the AWS Village all week. We've got the hardware there, the devices that I showed a little earlier, some of them are there. Oops. Okay. We've got some of the devices that are there. We've got some of the people who created it, so the inventors of some of the devices that are there are at the stage. There's also the talk from last year, which was NET402, where we went into more detail on the specific devices and some of the higher level systems like the automated remediation systems that we have. The other thing I want to say is every session is going to ask you to complete the session survey. The thing I will ask you that's a little bit different is the reason I'm here was feedback that we got last year for things that you wanted to see that we don't normally talk about. And so this is something we don't really do. Like the infrastructure is mostly invisible, but if you want to know more about it, you're interested in how the backbone works, how the internet edge works, these areas, please put that in the comments of your session survey, and then hopefully we can come back again next year with something else. But other than that, thank you all very much.